Okay, so this is going to be a video about optimization. Well, what is optimization? Optimization is something that it's a whole branch of mathematics. I'm just going to be touching on it because I've just learned it from a Calculus 1 perspective. So that is the level that this video will be at. Optimization is a branch of mathematics that goes into how to optimize spaces or how to minimize using amount of materials for a construction job, right? So you maximize your profits. There's all kinds of things that optimization problems can help you figure out and solve. And it's really cool because we're starting to see how a lot of the things that we've spent what seems like forever learning can be applied in the real world. So I'm going to do some problems here. And when you have an optimization problem, you're going to be given, let's read this problem and we'll look at it and then we'll take it apart. So it says, determine the dimensions of a rectangular solid with a base 3 times as long as it is wide, with a maximum volume if its surface area is 400 meters squared. Okay, so what is this even saying, right? There's so much information in that. And it doesn't, at the very beginning, it tells you we're going to be determining the dimensions of the solid. So that's the first thing. We're determining dimensions. And then when you look here, it says, so I've drawn a picture. You've been forewarned. I'm not the best artist, but this is supposed to be a 3D drawing of a rectangle. Okay? And so that's the first thing you want to do is draw a picture so you can kind of figure out what it is that you're doing. Now it says that this rectangular solid has a base that is 3 times as long as it is wide. So that means that this is 3x, and we'll call this x. And we call this x because this is the width. So we could have called it anything, could have called it s, but then this part right here would need to be 3s because it's 3 times as long as it is wide. Then it says with a maximum volume. So when you see a maximum volume, that means that this is the thing that we need to maximize. So it's going to be volume. Well, this is going to require you to know some equations, like what is the volume of a rectangle, a rectangular solid? What is the area of a rectangle? Things of that nature. How do you find surface area? Okay, so this right here, so we're going to be looking to maximize volume. So this is going to be when you see maximum volume or minimum area or maximum area, whatever is connected to what you're maximizing or minimizing, that's going to be what's called your primary equation. Okay? Your primary equation is the equation, let me write this on here. Whoops. Is the equation that you're going to be taking the derivative of. Okay. Now, let's keep reading. So, let's go ahead and let's do volume. So volume of this is going to be what? Length times width times height. There's our height. Let me do that in height. Okay. Now, we could go ahead and we could fill that in. So we have our length is 3x. Our width is x. And then we have height. But we have more than one variable. We have, these 2 variables here, and that's not helpful. We always want to try to get it down to 1 variable per equation. So since we have 2 variables, we're going to need another equation. And that is given to us when it says here, if its surface area is 400 meters squared. This is our constraint equation, our secondary equation. This is like you were born 5 feet tall. Your whole life, you're going to have to deal with the fact that you're 5 feet tall, right? We haven't figured out how to make you any taller. So that is your constraint. You're never going to be able to reach something that someone that is 7 foot would be able to reach, right? This is your constraint in life. These problems have constraints, and that's where we get our secondary equation. So let's do our secondary equation right here. And our secondary equation is that our surface area, which also equals 400 meters squared, we're going to go ahead and we're going to put that together. So how do we find surface area? Well, if we look here, that just means the entire surface. So if I say I have, well, you know I've got two of these, right? I have one on the front and one on the bottom. Well, how do I represent that mathematically? Well, there's two of them. So it's going to be 2 times 3x, which is the length, times the height. Do you see that? So we have this right here and this, right? So there's 3x times the height, and then we have two of them because we have one on the back. Plus, we have two of these sides here, which is going to be x times h. So we have two of those. Okay. And then, let me color that in. We can just, all right, we have two of those. And then we're going to have a top and a bottom. So this right here, there's a top and a bottom. And so that is going to be represented by 3x, because it's 3x long and it's x wide. So this is going to be 2, because there's two of them, 3x times x. And this is our equation that we are going to use. Our constraint equation is going to allow us to solve for one of these other variables. Now you could solve it in terms of x, and you could place the x in there. But I'm going to solve in terms of h. And this constraint equation is going to allow us to get what we need out of the primary equation. Okay, so let's go ahead and let's put some things together here. So if we distribute this, we have 6xh plus 2xh plus 6x squared. All right, and now we'll put together our like terms. And we know that surface area, is equal to 400 meters squared. All right, so if I go ahead and I'm solving for h over here, so I can plug it in over here. All right, so I have 400 minus 6x squared equals 8xh. Well, since I'm trying to get the h by itself, I'll divide this away. And this gives me my h, solving in terms of h. Okay, so now that I have this h, I'm going to plug this in here into my volume equation. So let's do that. So now I have volume equals 3x squared times, and actually we can go ahead and we can reduce this right here. You could take a 2 out of all of these, and that might make our work a little bit easier. Always see if you can reduce. So if we took a 2 out, that would be 200 minus 3x squared if I just reduce, and 4x. And remember, fractions are just ratios. So 1 to 2 is the same as the ratio 2 to 4. This is just a ratio. That's why we can do that. All right, so let's go back up here to our volume equation and finish this. So we have 3x squared times 200 minus 3x squared over 4x. Okay, so do you see but this is h. Actually, I'll just do it like this. So we know this is h that I plugged in. All right, so now let's come down here so we have a little bit more room. We will distribute in this x squared. So we have 200x squared minus 3x to the 4th divided by 4x. Now I can take this x and cancel it away, and then that'll leave me with 1x there and 3x's there. So volume equals 200x minus 3x cubed. And then I'm going to bring this 4 over here. I'm going to just pull it out because it's still in the denominator, and if I redistributed this, it would just look just how it was before, okay? So now that I have this set up equation for volume, now I'm ready to take the derivative of that. So v prime, now 3/4 is just a multiplier, which is one of the reasons that you want to try to set it up this way, because if I had it this way, I'd have to do a quotient rule derivative, and that's just extra work. So eventually, as you do these, you'll start to see where you can make your life a little bit easier. So if you did it the long way, nothing wrong with that. I feel like I take the long way with everything in my life. So if you do, that's fine, but here I just want to show you a way that I was shown to make this a little bit quicker. Okay, so now we have 200x minus 3x3. So if we want to take the derivative of that, that's going to be 200 minus 9x squared. All right, beautiful. Now what do? Well, now we have taken the derivative of the thing that we are maximizing, okay? And so now what we want to do is we want to set this derivative equal to 0. Well, what is going to make this derivative equal 0? 3/4 will never be 0. But this 200 minus 9x squared could make this derivative 0. So we'll say 200 minus 9x squared equals 0 when ... We'll move the 9x squared over. I have 200. So we'll divide this 9 away. And then we'll have, I'm going to switch this around just because I'm used to writing what equals something on the right-hand side. And I'm going to say I have to take the square root because this was squared, right? So I'm taking the square root. So I have to do that to the other side. When you take the square root of something, you have to do plus or minus. So it's going to be x squared equals plus or minus the square root of 200 over 9. Well, I'm not going to leave it that way. So we'll have plus or minus. That's the same as the square root of 200 over the square root of 9. Well, the square root of 200 is the same as the square root of 2 times 10. And square root of 9 is 3. Down here. So, 2 times 100. So we'll pull that. The square root of 100 is 10. So we pull that out. And we have 10 root 2 over 3. Oh, and I forgot the plus or minus. The reason I've just left out the plus or minus here is because with these problems, you're often going to get more than one answer. That when you have a squared, you're always going to get more than one answer, right? You have to do plus or minus. But one of them won't make sense. For instance, if we're trying to find the dimensions of this, you can't have a negative dimension. Okay, so the only thing here that's going to work is the positive answer. Okay? So, now we found x, which is great. But we need to find x. Oops. We need to find x. We need to find h. And we need to find 3x because we need to find what? The length, the width, and the height. All right. So we have one of our answers, which is this. So we have, that's 1. But then we need to say 3x. Well, what does 3x equal? That equals 3 times 10 root 2 over 3. That's going to equal 30 root 2 over 3, which then we will divide away this 30 and 3. So 3 goes into 30 10 times root 2. Oh, and we can't forget that this is in meters. Okay, so we have 3x up here. That equals 10 root 2 meters. And then x here equals 10 root 2 over 3 meters. Well, now how do we find h? Well, this constraint equation that we solved for h, so we could plug it in to our volume equation, so that way we would only have one variable. We now will take this x and plug it into this h equation so we can solve now for h. Okay, so let's bring this down here so we have some more room. And we're going to be plugging in 200 minus 3, and then our x is, let's just do our regular because we're going to be squaring this, or let's do our original. So if we have 200 divided by 9, and that's all square rooted, well, now when we square it, it is going to be just the regular 200 over 9, right? Because when you square a square root, it just becomes what was underneath the square root. But then we have 4 times, and then we'll do just regular old x, which we said was the square root of 200 over 9. So we'll just say 10 square root of 2 over 3. So these are all the same thing, but we're just going to plug it in to where it's easier for us to work with. Okay, so let's go ahead and distribute here. We have minus 600 over 9 equals 4 times 10 root 2 over 3, which you could simplify a little bit more. You can then say 200 minus 600 over 9 equals 40 root 2 over 3. Okay, and then there are several different ways that you can do this. I'm going to plug this into my calculator. You could simplify more. And make sure you're practicing on the calculator you'll be using on a test, because I have a calculator that I love that can handle putting this in all at once. And then I have the calculator that I'm allowed to use on a math test, which is just a regular TI-30X. And when I try to put in this business into a TI-30X, it freaks out and gives me the wrong answer, which might be a user error, but at least I know that. So what I'm going to do is I'm going to do the top first. Put that in my calculator, and the top gives me 133.333, right? It goes on and on. And then the bottom is 40 times root 2 divided by 3. Oops. And I get 18.856180083. Now I'm going to put it together in my calculator. I get that my answer for H is 7.071. Oh, we'll just look 067636, and because this isn't exactly accurate, I'll say it's 7.1 meters. So our dimensions are 10 root 2 meters by 10 root 2 over 3 meters by this height, which is 7.1 meters. So this is the dimensions that will give us a maximum volume with the constraint of our surface area being 400 meters squared. Now, say you're not allowed to use a calculator at all. Let's do it. Let's do H that way as well, since we did the other ones without a calculator. We'll say we have 200 minus 3 times 200 divided by 9 times 4 times 10 root 2 over 3. Well, I know that if I multiply this by 3, the top and the bottom, that's going to give me a 9, which will then make this guy right here cancel. There's a bunch of different ways you could do that, but this is the one that makes sense to me. So I'm going to say 3 times 200 is 600 minus, this becomes 9 over 200 divided by 9 times 12, because we're doing the bottom 2, times 10 root 2 over 3. All right, so then this is going to cancel, and I'm going to have 600 minus 200, and then I have 12 times 10 is 120 root 2 over 3, which I can then break down more. So we know 120 divided by 3 is 40 root 2, and 6 minus 200 is 400. And so if you say 400 divided by 40, that's going to be 10 root 2. And that would also be your answer if you don't want to go through the calculator jazz. But I like to show both ways because I was not always comfortable doing it this way. And to be honest, practice is the only thing that helps. Get used to being uncomfortable. And so that way, eventually you're like, these are just numbers and I can do some really cool things with them. You just have to learn the language, which is what we're all doing, right? Okay, so that is our very first optimization problem. Let's do another. Okay, so this example is somewhat like the last example. Let's look at it. So it says determine the dimensions of a rectangular solid with a base 1.5 times as long as it is wide, with a maximum volume if its surface area is 625 meters squared. So feel free to stop the video and try to work this problem on your own, and then come back and see how you did. Okay, so let's first determine our primary equation. Well, what wants to be maximized or minimized? Oops. Well, we see right here that we want a maximum volume. So our primary equation, which is the equation that we will be taking the derivative of and setting equal to 0 to solve for a variable, is going to be the volume of a rectangular solid, which is equal to length times width times height. Okay, well, what is our length and our width and our height? Well, we know that height is going to be right here, and then it says that the base is 1.5 times as long as it is wide. So we'll make the width x and the base 1.5 times greater than that. All right, so we can plug these things in. So we have v equals the length is 1.5x times the width, which is x, times the height. Now, again, we find ourselves with two variables, and that's not, what we would want here. So we're going to put these together, and we need to have a different equation that is going to allow us to solve for h. So we can plug it in terms of x and take our derivative. Okay, well, we are told here our constraint is that our surface area is never any bigger or any smaller than 625 meters squared. So let's go ahead and write our surface area equation. So we know, first of all, that surface area is equal to 625 meters squared. And surface area is, let's go over this. We have this front part, which is going to be right here. Well, there's also a back that's going to be that as well. So we're going to have 1.5x times h. Oops. Okay. Plus, then we're going to have these two sides, And the side is going to be equal to, oops, and I messed up. We have 2 of these, okay? And then we have 2 of the sides that are in green. So we have 2 times x times h. And then we have a top and a bottom. So right here and right here. And that is going to be equal to, oops, forgot my 2. There's 2 of them. So we have 1.5x times the length, or excuse me, yes, the width of x. So you see that we're going to have this and this. Okay, and that's for the top and the bottom. So let's go ahead and solve that. So we have 2 times 1.5, which is going to be 3xh plus 2xh plus 3x squared. And we know surface area is equal to 625. Well, what are we trying to combine here to find? We are trying to find h. So let's combine like terms. So we have 5xh plus 3x squared equals 625. I'm going to come over a little bit. 625 equals, oops, let's bring this 3x squared to this side. And then we'll divide by 5x, and that gives us h. So what I did here was I subtracted 3x squared and brought it over. And then I divided by 5x so that way we could isolate h. And now we have an equation that we can use. Actually, let me use a different color. Now we have an equation that we can plug in for h right here. So if we take our volume equals 1.5x squared times h, well, h is going to be 625 minus 3x squared divided by 5x. Okay? Now that we have our full equation with only one variable, we can take our derivative, or we could, but I don't want to do a quotient rule derivative and a product rule. Like that would be a lot of mess. That would just be a lot. So let's not do that. You could, but let's not do that. So what I'm going to do is I'm going to multiply this x squared in there. So we're going to have volume equals 1.5. Then we have 625x squared. Oops. 625x squared minus 3x to the 4th divided by 5x. Okay, well, this can go away because we're going to divide away that x. And this goes down to 3 because we took an x out. So we have volume equals 1.5. Now this 5 is going to come out here. Okay? Divided by, or times now 625x minus, oh, wait a second. Yeah, that's right. Okay. 3x to the third. All right, now we're ready to take our derivative because now we have some, look at how much better that looks than that. Like that would have just been a lot. Okay, so now we have a multiplier, which is 1.5 divided by 5. We don't have to do anything with him at all because he's just a multiplier. So let's take the derivative of the inside, which is going to be 625 minus 9x squared. And I'm going to keep doing this, I think, in this color because just see how this helps us. And this becomes 9x squared. Okay. So then this right here, you're going to need to plug into your calculator unless you want to do it by hand, but this isn't too hard for my calculator to handle. So it's 1.5 divided by 5, which is 0.3. Oh, and make sure you watch your notation. Make sure you're v priming it when you're taking the derivative, not before. So you have 0.3 times 625 minus 9x squared. All right, now we have to set this equal to 0. Well, 0.3 is never going to be 0. So v prime equals 0 when, when 625 minus 9x squared equals 0. Well, when does that equal 0? Let's move the 9x squared over. Then you get 625. Then you have 625 divided by 9 equals x squared. I'm going to move this over, swap my sides. Say x equals plus or minus, but remember that minus is not going to be useful because we're doing dimensions. Square root of 625 divided by square root of 9. Well, that'll simplify. So I always like to see if I got lucky and if there's a perfect square of 625, which there is. Square root of 625 is 25, and we know that the square root of 9 is 3. So this is one of our dimensions, which let's not circle that because that's not technically an answer. It is a dimension though. So we have right here that x equals, we'll just star it. So we have x equals 25, 3 divided by 3. Okay, but now we need to find these other two dimensions. We need to find the length, which is 1.5 times longer than x, and we also need to find h. All right, well, we've already solved for h up here, so let's go ahead and plug this in for h. So we have 625. We'll say, yeah, 625, I'll use blue. 625 minus 3 times, and we know that if you square 25 thirds, x squared, it's going to be 625 divided by 9, right? Because the square root, same thing with last time, we have the square root, and that's actually what x is, but when you square it, the square root goes away. Divided by 5 times, and then x, we can just leave it as 25 over 3, simplified. All right, well here, I'm going to multiply the top and the bottom by 3 again, because I want that 9 to go away. I don't want to use a calculator. So 620, I guess I would still have to use a calculator, but it's easier, I think, to multiply than it is to divide. Okay, so we have 1875 minus 9 times 625 divided by 9 over 15 times 25 divided by 3. Let's do equals. Okay. So then these are going to cancel, which leaves me with 1875 minus 625 divided by, what is 15 times 25? 15 times 25 is 375 divided by 3. Okay, and then 1875 minus 625 is 1250 divided by 375 divided by 3, which is 10 meters. So our height is 10 meters. So we have another star right here so we don't lose track of anything. Now we need to find the 1.5x. That's going to be 1.5 times 25 over 3. All right, so we have 1.5 times 25 divided by 3. And that gives us 12.5. And so our dimensions then are going to be 12.5 meters, don't forget your units, times 10 meters. Well, let's do width. That was length. I don't think it really matters. 25.3 meters times our height, which is 10 meters. And there you go. That's going to be your answer for this one. Okay, so what if you have a optimization problem that says a rectangle is bounded by the x-axis and the graph of f of x equals 4 minus x squared divided by 2. What length and width should the rectangle have so that its area is a maximum? Okay, so if we take this apart here, we see that we're going to need to draw a picture. So if we have a graph and we don't really know what's going on, it's helpful to graph this. So if we have just, there we go. And we'll say, we know that if we have f of x equals 4 minus x squared over 2, if we want to find our y-intercept, we're going to set the x's equal to 0. So that's going to be f of 0 equals 4 minus 0 divided by 2. That's going to give us 2. So we have a y-intercept at 0, 2. Okay? And then if we want to find our x-intercepts, we set our y, which is our f of x, equal to 0. So we're going to have 0 equals 4 minus x squared divided by 2. Well, this 2, if I was just multiplying it away on both sides, that's still 0. So 0 minus 4x squared, well, we have x squared equals 4, therefore x equals plus and minus 4. So now we have some points that we can graph. So we have 1, 2, 3, 4, 1, 2, 3, 4, 2, 3, 4. Okay, so we have a point at 0, 2, and then we have a point, which this is really small, I probably should have made that way bigger, at plus and minus 4. So we have a point here, and we have a point here. Now we could take the derivatives and we could find out where it was increasing and decreasing, and then we could look at the second derivative and see if our concavity changes, but we can also tell by looking that this is an upside down parabola. So let's go ahead and just put it in right there. And then we have, it says that we have a rectangle that is bounded by the x-axis and this graph. So we know that it's here, underneath of here. Now, what length and width, we don't know. And we want to know not only what the length and width are, but what they should be, so that way the area is a maximum. All right, so if we put, let's just say, well, we put the rectangle right here. Okay, there we go. And we'll call this 2x, and we'll call this y. Now, why did I call this 2x? Well, if we're looking at the distance from our origin, we have x direction this way, and we have an x direction this way. And since distance is never negative, I'm not going to say x plus negative x, it's just going to be 2x. And then we have y for our height. You could also call that h or z or whatever you want to, but I'll call it y. All right, so now let's look again. So we see as soon as they open up the problem here that our constraint is already given to us, right? Our constraint is given to us as 4 minus x squared over 2. And then we're also told that we need to find that the area is a maximum. So the area is going to be the thing that, I'm not going to use that color. I feel like it doesn't really show up well. Let's do this. So we have the area. Well, the area of a rectangle is just length times width. Well, we know the length is going to be 2x, and then we know the width is going to be y. Well, here we have found ourselves again having two variables, and we only want one variable, but we're given a restraint equation. And if you recall, f of x is the same thing as y. So we have f of x equals 4 minus x squared divided by 2. So we can plug that in. We have area equals 2x times 4 minus x squared divided by 2. And I'm going to do the same thing that I did before. I'm going to distribute this x. And so I have a 2, and then I'm going to have a 4x minus x cubed. And then I'm going to bring this other 2 right here out. So it'll just be a multiplier. So then I have that area, well, 2 over 2 is just 1. So then I have 4x minus x cubed is my area equation. But remember, we want to simplify as much as possible before taking our derivatives. So what do we have in common here? Well, we have an x, so let's pull that out. And then we have 4 minus x squared. So I see after I did this that that's going to make my life more complicated. Then I'm going to have a product rule derivative. So this one is actually the better one to use. So just play with it and see which one makes it easier for you to take your derivative and then for you to set your derivative equal to 0. Okay, so let's do this. We have a prime equals, well, the derivative of 4x is 4, derivative of x cubed is 3x squared. All right, beautiful. Well, now we need to find out when this derivative equals 0. So a prime equals 0 when ... 4 minus 3x squared equals 0. So that happens, here we go, 4 divided by 3 equals x squared. Well, then we have x equals square root of 4 over 3 plus or minus, but we know now that the plus is all we're going to be dealing with because we're talking about dimensions. Can't have a negative dimension. All right, so x equals, well, square root of 4 is 2 over, and then square root of 3 is just square root of 3, which I think is like 1.7 something, but it's easier just to write as 2 divided by square root of 3. Let's not circle. Okay, so we'll put a star here. All right, so now we know x, but these are not our dimensions, right? For our area. We want to know 2x and we want to know y. So we know x. So now if we say 2x, that'll give us 2 times 2 square root of 3, which gives us 4 square root of 3. Because remember, there's like an invisible 2 over 1 right there. So if you multiply these through, it would be 2 square root of 3. Okay. So that is our length. Well, now, what is our height? Well, we know x now. Right here, we found x. And we have our, now we go back to our constraint equation. And we are now going to plug in for x what we found, and then we'll get our f of x, which remember we said equals y. So we have f of x equals 4 minus x squared over 2. So we have 4 minus 2 over square root of 3. Well, actually, let's do what we did before. So we have here that this was originally what we got for x, which was 4 over 3, and that's under the square root. Well, if we square that, square root goes away, and we just have 4 over 3 divided by 2. Okay, so if you take 4, that's the same as saying 4 over 2 minus 4 over 3 divided by 2. So If you have 4 over 2, you know that's 2. And if you have 4 over 3 divided by 2, that is going to be the same as multiplying times the reciprocal of 2 over 1. So we have 2 minus 4 over 3 times 1 over 2, which is going to give us 4 over 6. So now you have 2 minus 4 over 6. And then we're going to need to get a common denominator, so let's just multiply by 6. So then we have 12 over 6 minus 4 over 6. That gives us 8 over 6 equals y. Okay, so here we go. It says the question asked us to find the length and the width. And here we have that our length, which is 2x, let's do is 4 over 3, so this is our length. And then our width is our y, so our dimensions are 4 square root 3 by 8 over 6, which reduces, we divide that by 2, we're going to get 4 over 3. And this is the length and width of our rectangle. So our rectangle is with a maximized area with the constraint of being bounded by the x-axis and the graph of f of x equals 4 minus x squared divided by 2. Those are the dimensions of our rectangle that will maximize the area. So let's do another problem that's like that. Here we have, it says a rectangle is bounded by the x-axis and the graph of f of x equals 6 minus x squared divided by 2. What length and width should the rectangle have so that its area is a maximum? Round your answers to 2 decimal places. Okay, so the very first thing we're going to do is draw a picture to determine really what information we're given here. Let's use blue. All right. Now, in order for us to graph this here, it says that our rectangle is bounded by the x-axis and this graph. So the graph of f of x equals 6 minus x squared divided by 2. So let's write that down. All right. So if we're going to graph this, let's go ahead and let's get our y-intercept, which is when x equals 0, right? That's what our y-intercept is. So we have 6 minus 0 squared divided by 2. Well, that's going to be 3. So we have a 0 for our x and a 3 for our y. So this is our y-intercept. So if we have, let's see, 1, 2, 3. Okay, so we have right here, this is our y-intercept. And then now let's get our x-intercepts. And so we have, that'll be when y equals 0. Same thing here, multiply, that goes away, that's still 0. So 6 minus x squared equals 0 is what we'll be working with. Then we have 6 equals x squared. And then we have the square root of 6. We have plus and minus square root of 6 equals x. The square root of 6 is like 2.4 or something, so almost 2.5. So we'll have plus and minus that. For our x-intercepts, that's 1, 2, like 2.5, right? There we go. And also you can tell from this graph that this is going to be an upside down parabola, right? Because you have that negative x squared. So let's go ahead and connect our dots. Okay. So now that we have an idea of what our graph looks like, we can go ahead and put a rectangle underneath. Now, when we look at the question, it says, what length and width should the rectangle have so that its area is a maximum? So the thing that is talking about being maximized here is our area. And the thing that's going to be maximized is going to be what we take the derivative of. That's going to be our primary equation. So if we're maximizing our area, that means we want to take up as much area as possible, right? And we're also going to have symmetry here because of this being a semicircle. Okay, so there is our rectangle. And let's see, we have this point here that's going to describe our x direction and our y direction, which we can call xy. But if you see down here, we have these two x's. Well, why do we have the two x's? Because this is our distance, x, a distance, x, represented, you could make it p or whatever, but we'll call it x, from our origin. And so that's why we call this whole thing 2x, because we want to know what the entire x distance is. So we will represent that by 2x. So you really could look at this right here as 2x y, right? Because you're not just putting in x, but that's not exactly correct to say 2x for right there, because xy is really just a point. We're just also using x as, as our variable to represent our distance. Okay, so the very first thing we need to do after we have drawn a picture, so one, we draw a picture, right? Draw a picture and we label everything that we're given. So we label everything given. And if we see here that our x, we don't know what this distance is, but we do know that f of x is the same thing as y. And because f of x is the same thing as y, this point is also like saying x, comma, and then your function, 6 minus x squared divided by 2. Okay? All right, so the second thing that we'll do then is going to be to identify our primary equation, aka the thing that is being maximized or minimized. And we see that we're asked to find a maximum area. So we know it's going to be area. Well, the formula for the area of a rectangle is length times width. But we see here that the length is represented by 2x and our width is represented by y. So let's go ahead and plug that in. So we have 2x, y. All right. And we find ourselves in the same situation as before, where we have more than one variable and we only know how to take a derivative of one variable. So now we are going to step 3, which I could do these in different colors to make it a little bit more obvious and fun. Okay, so now we need to identify our secondary, aka constraint equation. So again, the thing that we have to live with, even though we're told to maximize this, we have to maximize it with certain restrictions. Okay, so let's see, what is our secondary equation? So it tells us here that our rectangle is bounded by the x-axis and the graph. So bounded, it's restricted, it's constrained. So looking for words like bounded or if, and we'll see that in another problem, you'll start to be able to recognize, okay, well, that's my secondary equation. Well, this one's really nice because we don't have to figure it out like with surface area or perimeter. It's just given to us. This is our secondary equation. So let's write that down. F of x equals 6 minus x squared divided by 2. But remember, we said that f of x is the same thing as y. So we're already solved for our other variable. All right, so after we've done that, our next, we'll say step 4, we are going to plug our secondary equation into our primary equation. So we have a equals 2xy as our primary. So now we're going to plug in our secondary equation, which was 6 minus x squared divided by 2. And then we're going to solve. So we have a equals, now what I want to do is I want to take this and I want to distribute this x, because right now, remember, the whole point of this is to take the derivative of the thing that we're maximizing or minimizing. And so I want to get this into a form that is so easy to take the derivative of. So right now, I would have to do like a quotient rule and a product rule, and we don't want to do all that. So what we're going to do is we're going to distribute this x, so that way we can just have a multiplier here and avoid all of that. So we're going to have 2. We're going to distribute that x back in, so we have 6x minus x cubed, and we had divided by 2, but I'm just going to pull him out as a multiplier. So that leaves us with a equals 2 over 2 is just 1. So now we have 6x minus x cubed, and that is super easy to take the derivative of. All right, so let's say step 5 is to take the derivative of primary equation. All right, so let's do that. So we'll say a prime equals 6 minus 3x squared. Beautiful. Okay, so after we've taken the derivative, now we are going to set our derivative equal to 0. All right, and solve for x, right? So we're going to find out what makes this solve for x. Oops. Okay, so now we have a prime equals 0 when 6 minus 3x squared equals 0. We're going to bring that 3x squared over. We have 6. Then we're going to have 6 divided by 3 equals x squared. That is going to leave us with x equals square root of 2. So we have plus and minus the square root of 2. So now we have x. We have, let me bring this, bring this down. We have this right here. We have x. We have x, but we need 2x, right? So let me bring this down. Okay, here we go. All right, so we need 2x, so we're not done. So here, if we take 2 times the square root of 2, that's 2x, right? And that's our answer, 2 square root 2. So this is our maximized length, right? So remember we had that point up here? Well, our x is 2 root 2. Now we need to find y. So that'll be our next step. We'll say we'll just use red. Okay, so step 7 is to plug this value of x, not the 2x, but the actual value of x right there, into our secondary equation to solve for our other variable. Okay, well, what was our secondary equation? Our secondary equation, whoops, was this right here. So we have f of x, which now we're going to plug in root 2, equals 6 minus, well, root 2 squared is just 2, divided by 2. So that's going to be 6 minus 2, which is 4 divided by 2. Oops, so that's going to give us 2. So our y equals 2. So we have a length of 2 root 2 and a height of 2. And I believe this was, just wants the point, so we're not doing meters or anything like that. Okay, so our answer then is 2 root 2 by 2, or you can even say, I don't know why I put a comma right there, looking at the point. So that is what our maximized length and width would be to get a maximum area. Okay, so let's look at this. If you have a problem that says find the point on the graph of the function f of x equals square root of x that is closest to the point 6, 0. Okay, so when you see closest, you know that that's going to be minimizing, right? We want to minimize something. Well, if we're saying closest, we're going to be minimizing distance. Okay, just as an aside. But let's start with our very first step of drawing a picture and labeling everything that we see. Okay, so we're given that the graph of the function is f of x equals square root of x. Okay, so what is that going to look like? All right, so we have f of x equals the square root of x. Well, let's just plot some points. So let's say we have f of 1. Well, square root of 1 is 1, so we have a point at 1, 1. Let's go 1, 2, I'm going to make this quite a bit longer. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And we'll go 1, 2, 3, 4. Okay. All right, so we have one at, I don't know why I put a 0 right here, at 1, 1. So we have a point right there. Now what if we do f of, let's do f of 4 equals square root of 4. And that'll be 2. So we have a point at 4, 2. So we have 1, 2, 3, 4, 2. Right about there. Now what if we have f of 16? Well, the square root of 16 is 4, so we're going to have 16, 4. And I think I made 16 down here. I think that's where my 4 is. It's about, right? So let's go ahead and we'll connect our dots. And then also if we did f of 0, square root of 0 is just what? 0. So we'll have a point at 0, 0. So we can also do that. So this is what your graph is going to look like. So it's really helpful just to see what is going on. All right, so the second thing that we're going to do, number 2, is we're going to identify our primary equation, which is going to be the thing that we're taking the derivative of. All right, so like I said, it says up here that it's closest, so we're going to be minimizing and distance. Well, all we're given is that we're closest to the point 6, 0. But when you see minimizing distance, you're going to think of the distance formula, right? The distance formula is d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. All right, so, well, where do you plug these things in? This is going to be our x, and this is going to be our y. So we'll do it like this. 2 equals the square root of, we'll make it x1. So we'll say x2 minus 6, and we'll do it the other way to show that it doesn't matter which one that you choose. So we'll say x2 minus 6 plus y2, which is going to be y2, minus 0 squared. So d equals the square root. Now if you FOIL these out, which is what we'll have to do, you're going to get, let's do a little thing down here, squared. You're going to get x to the, oh, that's not an x squared, that's an x2. So we're going to have x squared minus 6x minus 6x plus 36. So this up here is going to be x squared minus 12x plus 36 plus, and then when you do y minus 0 squared, you're going to get y squared minus 0y minus 0y, right, times 0y. So all you're going to get, say, well, that'll still be minus 0y. So those just go away because they're all multiplying by 0. So you're going to get y squared. Or not y squared, y2. So we'll just leave it as y. Or is it y squared? It is y squared. Okay. Do you see that? Because it goes y times y. There we go. Sorry. Got a little thrown off by the twos. It happens. All right, so let's erase this here and give us some more room to work. And so now we see that we have gotten to the point when we are identifying our primary equation where we have more than one variable. So now that we've done that, we need to, third step, identify our secondary equation. And solve for our other variable, which in this case I'm going to solve for y. Okay, so our other secondary equation, aka our constraint equation, we see that we're given it because it says this is our graph of this is our function, so that's our constraint. So let's write that down. F of x equals the square root of x. So we know that f of x is the same thing as y. So y equals the square root of x. So they made it easy for us here. And we're going to go ahead and plug that in. So actually, before we plug that in, I want to show you that it doesn't matter which way, like if you choose for your points to be x1 or x2. Let's go ahead and show that. Excuse me. So if I have this, let me move this down here. Give us some room. Because I think it's important to understand that. Okay. So we'll do this in pink so we know. So if we have square root of, I'll do a little line. And we say, now we'll call this x2 minus x1 squared plus, we'll have y2 be that, oops, minus y1 squared. Well, when we square the 6 minus x, we're going to get 36 first, then you have your outers, minus 6, your inners, minus 6, your last, plus x squared. Do you see how that's the exact same thing? Ooh, I forgot the x's. Okay, so we just get it backwards. We get 36 minus 12x plus x squared. And if you see, that's the very same thing as this. It's just in a different form. The 36 and the x squared have been swapped. And then we'll see the same thing over here with 0 minus y1 and 0 minus y, whatever. We'll call it y, not y1. Okay, and so then we have 0 first, outers minus 0y, inners minus 0y, and then plus y squared. So you see that all of those go away because they're 0 and you just have y squared. So you would end up with the very same thing. Okay, so I think that's important to see. All right, so then we'll go back to right here. And so now we've identified our secondary equation. And the fourth step is to plug your secondary equation into your primary equation. Okay, so let's go ahead and do that. So we have that our primary equation was d equals the square root of x squared minus 12x plus 36 plus y squared. So we're going to plug in, we have x squared minus 12x plus 36 plus y, which is square root of x squared. Well, when you square that, you're just going to get x. So let's go ahead. Now we have d equals x squared minus 12x plus 36 plus x. And let's simplify. And so we're going to have x squared minus, when you have a minus 12x plus an x, you're going to get minus 11x plus 36. Okay. So now that we have simplified, let's see, is this as simplified as we can get? Because if I do, is this, yeah, I think so. I think that if we take the derivative this way, let's put it in this form. We'll go x squared minus 11x plus 36 to the 1/2, because that's going to be easier for us to take the derivative of than having it under the square root, because it's easier to see that we're going to need to bring that down. All right, so the fifth step is to take the derivative of the primary equation. Okay, so we have that d equals 1/2 times, and then we're going to write this the same as it was because this is a chain rule derivative. And remember, that becomes negative 1/2 because we have to subtract 1 times the derivative of the inside, which is going to be 2x minus 11. All right, so let's look at this here. Oops. Don't forget your notation, d prime. All right, so what I have right now is a 1 over 2, and this 1/2 goes back into the bottom here. X squared minus 11x plus 36 times 2x minus 11. Now, if you're looking at this, of course we want to simplify. You may be tempted to cancel these 2's, but don't do that because we haven't factored out a 2. The only time you cancel is if we factored something out, and we haven't done that here. So I'm going to erase this 1, but I just wanted you to see that that's where our 1/2 was, and that's where this 2 in the bottom comes from. And this 2, I don't know if this is going to work. It's a lightsaber. This 2, I'll do red. It's fine. So we have this 2 right here. That's this 1/2, sorry. I'm going to have to go back to the pointer. The lightsaber is distracting. It's cool. It's distracting. Okay. So anyways, and this -1/2 is what we've done. We've moved this because that negative just says that all of this is in the denominator. All right, so now we have our derivative. Well, now, step 6, let's see here. Let's do, this color. Step 6. Now we're going to set our derivative equal to 0 and solve for x. Okay, so we are going to have, now what you want to do is the only thing that can make this derivative equal 0 is the top. This 2 is never going to be a 0. This is never going to be a 0 because it's plus 36. But anyways, you always just want to, for these, you want to focus on the top. Technically, it's where your derivative is also undefined, but your derivative is, we don't need to worry about that for this. So you just want to make sure that your numerator, where it is equal to 0. So this is going to equal 0 when 2x minus 11 equals 0, which is going to be 2x, and we'll have 11, and then we'll have 11 divided by 2 equals x. So now we have, which we won't circle, but because that's not one of our full answers, is it? Let's see. It said to find the point on the graph. Okay, so that will be. So what we're trying to do then is find a point, x, y. So this is one of our answers. This x is one of our answers. Well, I've already got it right there. Just keep track of them. All right, the next thing you want to do is take that value of x and plug it in to your secondary equation. To solve for your other variable. Do you see how it's the same steps? You may have other things you need to do, but it's always the same steps. To solve for other variable. In this case, our other variable is going to be y. All right, so our secondary equation was f of x equals the square root of x. All right, so now we have f of 11 over 2, and that's just going to equal the square root of 11 over 2. Now, technically, if you have a professor that doesn't like, because this is the same as having square root of 11 over square root of 2, and some dead Greek guy or some dead guy said that we can't have roots in our denominator, which I'm sure I've done other ones where I think the last one I left it in there too. But you can rationalize this by just saying square root of 2 over square root of 2, which is the same as multiplying by 1, so it doesn't change anything, just makes someone else happy. And then you have square root of 22 over 2. So our dimensions then, here our answer is that our point is 11 to square root of 22 over 2. Bam. Okay, so this is a problem, the Norman window problem, that you'll see in a lot of textbooks and possibly even on your test. So, a Norman window, if you're interested, I'm pretty sure, because I Googled it, it said that a Norman window, it's just called a Norman window, because I was like, why is it called that? Does it have some mathematical significance? It doesn't. Apparently, this is just an architecture type that originated in Normandy. So it's called a Norman window, if you wanted to know. Okay, so back to the math. It says, a Norman window is constructed by adjoining a semicircle to the top of an ordinary rectangular window. So we have that. We have our semicircle here, and we have our rectangle there. And it says to find the dimensions of a Norman window of maximum area if the total perimeter is 14 feet. All right, so first thing we're going to do is draw a picture, which I already drew this part of the Norman window. We're going to call this Y. All right, now let's do the very first thing we would do, like I said, is to draw a picture. We drew our picture. Second thing we're going to do is identify our primary equation, which is what? The thing being maximized or minimized. And this will be the equation that we take the derivative of. All right, so if we look here, it says find the dimensions of a Norman window of maximum area. Okay, so we know that we're doing something with area. Well, normally what we do is just take the area equation for a particular shape, but we don't have just one shape here. We have two shapes. We have a rectangle and a semicircle. Well, if you are like me and you didn't remember your equations for a circle, I found, cannot take credit for this, but I found this online, and there's this mnemonic that says, let's see, where should I draw this? I'll do it over here. It says cherry pies. Oh, hold on. Go like this. That's the C. Cherry pies. Delicious. Apple pies. Whoop. Are 2. See what we're getting at here? Okay, so this is for circles. All right, so this is telling us that the circumference of a circle is equal to pi times d. Well, we know that d is just 2 times r, right? We know that this is just 2 times the radius, because right here we have a radius. Whoops. Or you could even go like this, and that would be your radius. Well, another one of those would be your full diameter. So that's just 2r. So this equals 2 pi r. So that's how you can remember the circumference of a circle. Pretty cool, right? Now, what about the area of a circle? Well, here, apple pies are 2. So we have apple for area, pi r squared. Bam. That's cool, isn't it? I think that's so cool. So whoever came up with that, awesome job. Okay. So anyways, now that we have remembered that this is the area for our circle, the pi r squared, we can realize that we don't have a full circle here. We have a semicircle. So the area of this circle is going to be the area I'll put of a semicircle is going to be 1/2 of the normal area of a full circle, right? And then we know, we've worked with this a few times in this video, that the area of a rectangle is just our length times our width. All right, so that means that in order to find the area of this entire shebang, we have 2 areas to work with. We have our length times our width plus 1/2 pi r squared. But I tell you what, instead of using r, what I'm going to do is, because I want to relate this in a way that the dimensions of our Norman window are relating to each other, so we don't make our life, we don't give ourselves another variable and then require another equation which we don't have to solve for. So if we look here, this we could call x. Do you see that that is half of our length? It is. You see it? Yep. So we can call this, I'll do this in a different color. this whole thing is going to be 2x. Because half of that is 1x. Okay, so we're going to have area equals, our length is 2x, our width is y, and then we have 1/2. Now our radius here, we went ahead and made it in terms of x because it's the same length as half of our length of the bottom of our window. So we'll say pi x squared. Beautiful. But we still have something that we have to work with because yet again, we find ourselves with more than one variable. So what do? That's okay. We go to our constraint. We use our constraints in life to get creative, to help us, right? That's what we do in life. So let's do that here. So we are going to step 3. We are going to go to, there we go. I probably don't want to block myself off actually there. So I'm just going to move down some. So step 3, we're going to identify our secondary equation aka our constraint, the thing that we have to live with. Our constraint equation, and then solve it for our other variable, which you could do any of the variables, but I'm going to do y because if you look here, we have x here, and I don't want to have to plug in extra stuff. So let's be more efficient, but you can do either one. All right, so our secondary equation, let's look back at our question for this. If I can get my thing to move down some. Okay. Whoop. So it says here, a Norman window is constructed, we know that. Okay, so find the dimensions of a Norman window of maximum area, that was our first primary equation, if the total perimeter is 14 feet. When you see if, you know that you're working with a constraint. That's like someone says, you can do this if you have $500. That's your constraint, right? Or you can ride this roller coaster if you meet the height requirements. They're just things you have to live with, things you got to do. Okay, so if the total perimeter is 14 feet, so we know that we're looking for the perimeter. All right, so perimeter here is going to be equal to 14 feet, but that's not our equation. That's just what our equation equals. So when we look here, well, we know that the perimeter of this is just going to be the sum of the distance around, right? So for a rectangle, we have this side, this side, this side, this side, but it's only the distance around. So normally for a rectangle, we would say it would be this way, this way, this way, this way. But all you want for perimeter is how much you have to go around for the outside. So this guy isn't gonna count. For our perimeter, we're just gonna do right here, and right here. Okay, so we know that the perimeter for this part, for the rectangle, is gonna be 2 of those y's plus 2x. But we're not done because we still have to walk around this semicircle. Well, we know that another word for the perimeter, the distance around, aka the distance around a circle, is circumference. And we know that. We know that this is going to be pi times d, which we could say pi r squared, which then we could also say, or excuse me, not pi r squared, but 2 pi r, those 2's. So what we're going to do then is we don't have a full circle to walk around, we only have half. So we're going to say plus 1/2 the distance around a full circle, which we said would be pi d. But remember, d is just 2 times r. And since it's 2 times r, we can just write this as 2 pi r. You could also write it as pi 2r, but we're so used to seeing it as 2 pi r that we'll write it that way. Okay, now we have this equation, and what we're going to do is, oops, remember we're also doing that as x. We made r x. All right, so now we look at this and we realize that this and this, those 2's will cancel, so that simplifies some. So now we have 2y plus 2x plus pi x. There we go. But we realize that we have this y, so we want to go ahead, because that's what we're solving for up here. So let's solve in terms of y. Well, we know that the perimeter was 14, so let's rewrite the whole thing. Plus 2x plus pi x. And then we're going to have 14 minus 2x minus pi x equals 2y. Well, we still need to divide away that 2, so we're going to divide this whole thing by 2. All right. So there we go. This is going to be our secondary equation. So I'm going to erase him, we know he's just, well, maybe I shouldn't do that in case we look back. All right, so I'll rewrite him then. We'll have 14 minus 2x minus pi x divided by 2 equals y. So this is our secondary equation. All right, so step 4. Whoop. Plug your secondary equation that we just found and solve for into primary equation. And then solve for x. All right. So our primary equation was a equals 2x times y. Well, we know y is 14 minus 2x minus pi x divided by 2 plus 1/2 pi x squared. Well, we see that these 2's will cancel, and then that'll give us a equals x times 14 minus 2x minus pi x plus 1/2 pi x squared. All right, so now let's put everybody together. And we can do 14x minus 2x squared minus pi x squared plus 1/2 pi x squared. All right, well, we can further simplify this. We have some like terms here. We have pi x. Well, when you have a full pi and he's negative, you got a negative full pi plus half of a positive pi, that's going to leave you with negative half pi x squared. And then you have 14x minus 2x squared. Okay, so can we simplify this any more before we take the derivative? I think it's in good shape to take the derivative. So let's go ahead and do that as our next step. Say step 5 is take the derivative of your primary equation. Okay, so we have a prime equals 14. The derivative of 14x is 14. Derivative of negative 2x squared is going to be negative 4x. And I did that by just saying, you know, negative 2, bring down that power, and then you have x. That leaves us with negative 4x minus 1/2. We're going to bring down that power of 2, and we get pi x to the first. These guys are going to cancel. So our a prime equals 14 minus 4x minus pi x. And that's your derivative. Okay, so after you have the derivative, you need to set your derivative equal to 0 and solve for x. Okay, so we have that our a prime equals 14 minus 4x minus pi x, and this equals 0 when, 14 minus 4x minus pi x equals 0. So let's move, well, I don't need to write the plus, 4x plus pi x over, and then we have 14. Well, let's pull out an x here, and then we're going to have 4 plus pi. We have 14, so if we divide away this 4 plus pi from both sides, we are left with x equals 4 plus pi. All right, so I'm going to bring down this window here that we drew. Bring them way down. All right, clean them up a bit. Okay. Redraw that x. Oh, now he's... Okay. So we know that 1x is the 14 plus 4 pi. So we know that that is our radius, right? So we have 2x, though, that we need to figure out. So this is our length. We're going to say 2 times 14 over 4 plus pi. And that's going to give us 28 over 4 plus pi. Now you may say, well, okay, I'm going to divide this 4 away, but you can't. You cannot divide that 4 away because this is not 4 by itself. It's 4 plus a little bit, 4 plus pi. So these guys are together. All right, so we have this right here is one of our answers. So we have this part is 28 divided by 4 plus pi. And this guy up here is 14 divided by 4 plus pi. Well, we still have y left. What is he? All right, so what step were we on? 7? All right, so now we're going to plug our value of x that we found into our secondary equation. And solve for our other variable. Okay, so what was our secondary equation? Our secondary equation is up here somewhere. Oh, I moved stuff all around. Goodness. So it's going to be this part. Oh boy, that's not what I wanted to do. One day. Hopefully I already got that down because I'm not going to try to correct it. Whoop. Okay. Maybe one day I'll get better at the Zoom thing. Maybe not. Okay, well I have it right here. I'm going to rewrite it. So our secondary equation was 14 minus 2x minus pi x divided by 2, whoops, equals y. All right. Well, we're going to plug in our y values, or our x values. So 14 minus 2 times our value of x, which we said was 14 over 4 plus pi. minus pi times x, which we said was 14, 4 plus pi, divided by 2. Well, we need to get a common denominator. So we're going to say we're going to multiply the top and the bottom by 4 plus pi, because that's the same as multiplying by 1, equals y. Okay. So when I do that, this is what we'll get. We're going to get 14, 4 plus pi, and then these guys are going to cancel. So you're just going to have 2 times 14, which is 28. Minus, well, this guy's going to cancel, and you're going to have minus 14 pi divided by, and then you have 2 over 4 plus pi. All right, equals y. So let's go ahead and distribute here. So 14, let's divide everybody by 2. Because you see here, we can pull out a common factor of 2 up here. So let's do that. So we have 2, we'll have 7 plus, oh no, not plus, 7, 4 plus pi, minus, lies, 14. 2 times 14 is 28, minus 7 pi, over 2 times 4 plus pi, equals y. All right, so now we see that these 2's will cancel, and we're left with 7, 4 plus pi, minus 14 minus 7 pi, over 4 plus pi, equals y. All right, so let's distribute. So that is going to be 28 plus 7 pi, minus 14 minus 7 pi, over 4 plus pi, equals y. Well, we see here, these 2 go away because it's a plus 7 pi and a minus 7 pi. 28 minus 14 is 14. I don't know why I put this together. It's supposed to be 4 plus pi. And then we have a denominator of 4 plus pi equals y. And you could put that in your calculator, but I'm not going to. Or leave it as exact as possible. So our y then is 14 divided by 4 plus pi. All right, so that means that the dimensions of this window are going to be, so I'm going to write it all down so it's all together. We have x equals 14 divided by 4 plus pi, 2x equals 28 divided by 4 plus pi, and our y is 14 divided by 4 plus pi. So you see that this is actually the same height as half of this is long. And these are our dimensions for the Norman window. And it seems like a lot. I want you to look at everything we just did for this one problem. But it's not bad when you follow the steps, when you understand the process. You can do this. You can absolutely do it. Practice, practice. All right, I hope this was helpful.